So what is this? We're going to kind of review a little bit of what we did before. Was ist das? What is it? Name it for me. Talk to one another. Tell somebody sitting near you. Don't yell it out. What is it? Free body diagram? Did I hear free body diagram? I think I heard free body diagram. And to be completely correct, I should label these. So force of gravity, and we'll say maybe that's 300 newtons. And this could be the force from the floor, because we don't know the name of that yet. And we'll make that 300 newtons. And this, let's say, is the force of, who do I want to pick on today? Force of rock. And we'll make this 250 newtons. And we'll put that at like 15 degrees above the horizontal. So, what could be happening here? What's an explanation for the forces we're seeing on this object? Go for it. Kicked, pushed, upward. He could be pulling on it with a rope. We don't really know what's happening beyond the forces we see. This could be an object that he's kicking upward in an angle. We've done lots of kicking problems with projectile motion. We don't know how big this is, so maybe this is a gigantic box, and Rock is doing his very best to push it, but it's so big that he's sort of pushing up on it as he goes. We don't really know how big this is. Or maybe he's been shrunk. I don't know. We don't know if this is a box that he's pulling along like a dog on a rope with a string attached to it. We don't know. And it doesn't really matter. But free body diagrams are the way that we understand the forces in the situation. So what we're going to start doing today is a little bit of math with free body diagrams. So we're going to start off talking about the law of inertia, Newton's law of inertia. And what this has to do with free body diagrams is this. Here's a box. Before we set Rock to work pushing on this thing, force of the floor, 300 newtons. Force of gravity, 300 newtons. Oh, that's a terrible color contrast, isn't it? I'm sorry. Let's shrink that up a little bit. There, that's better. This thing is at rest because the forces acting on it are all balanced, and until we unbalance the forces, so it shall remain. You know this intuitively. You talked about this conceptually probably in physical science, and now we're going to do all the math behind it. So when we, the sort of official wording for Newton's first law, an object remains at rest, and an object at rest remains at rest, object in motion remains at motion with constant velocity unless the object experiences a net external force. And the word that I want to draw your attention to most strongly is net. That's a pretty important word. So I'll underline it in 3 different colors. So to sort of rephrase that, if the net external force on an object is 0, acceleration is 0. If acceleration is 0, does that mean the object is not moving? Not necessarily. How could it have 0 acceleration but have non-zero velocity? Talk amongst yourselves. Talk at your table. I did hear a few people muttering, constant velocity. Yeah. If something is moving at constant velocity, it's got 0 acceleration. So we can have an object that has all the forces on it balanced. The net external force is 0. It's got 0 acceleration. So you're sitting still-ish. Some of you are twitchers or jigglers or fidgeters, and that's okay. I am too. But if you're sitting in your chair, is anybody here currently spontaneously floating up into the air? No? Well, you're just not trying hard enough. Anybody spontaneously sinking down through the floor? Paying a visit to Mrs. Berger? No? Okay. Then on the y-axis, the net external force on you is 0. You really want it to remain that way. That means the floor is continuing to support you. This is a vector sum. So when we did, I'm going to shrink this up a little bit. When we did all that motion stuff, and we had people going this way and going that way and then going this way, and we figured out their resultant displacement, guess what? We're going to do the same thing for forces. It's so exciting. We're going to find the net, the sum of all those vectors. So let's do a really simple one together. I got a box. We have a lot of boxes. We'll start with a very, very easy one. We have force of gravity on this box equal to 556 newtons. We're going to assume that this thing is not rising up into the air or sinking through the floor. Therefore, the force of gravity on the box, or the force of the floor upward on the box, has to be equal to gravity. Right now, on the y-axis alone, what's the net force on this object? 0. Because we've got 556 up, 556 down. It's not sinking through the floor. It's not rising into the air. What if we add to that, let's use a different color, and we'll make this force of eddy of 428 newtons to the east. Now, when I asked you for the y-axis net force, you can look at that and you immediately go, well, it's 0, they're equal, duh. But what we're going to start doing is sums of forces on the two axes. So I'm going to introduce you to one math sign. You may have already seen this, I'm not sure. I do a bad job drawing it. That's sigma. It's the Greek letter sigma. And it is used in math and science to represent sum, the sum of a series of values. So we write sum of forces on the x, sum of forces on the y. Let's go ahead and do the sum of forces on the y-axis for this object. Okay, so the sum of forces on the y-axis simply equals all the forces up minus all the forces down. And I very often, especially when I'm sort of warming up to these problems, I mean, I do them every year, but right now it's been a year since I've seen these, so I'm still warming my brain up to them. I tend to write that first. Right now we're going to start off dealing with situations where there's one force up, one force down. We will get to situations pretty quickly where we have multiple forces up and multiple forces down. And so I kind of like to remind myself, you know, it's not just force of gravity and force of the floor. Any force up, any force down, and that's my trick so that I don't screw up and forget a force, because God forbid you forget a force, everything goes haywire from there. It's terrible. So what forces up do I have? Well, I have force of the floor, and I have force of gravity. Now, why is it so important to draw a free body diagram first? Oh, because that's what's going to show me what all my forces up and all my forces down are. That's what's going to give me the visual on what every single force that I'm dealing with is. Now, in one this simple, could you do it from just text? Probably. Rapidly, they will get more complicated, and you will not be able to do it from text alone. Okay, so in this case, sum of forces on the y equals 556 newtons minus, and I'm gonna write, because this is a vector, I'm gonna write up minus 556 newtons down, and sum of forces on the y for this object equals 0, which we already knew. Duh. Like I said, these are simple. They're going to get more complicated pretty rapidly. So let's go ahead, we'll set that aside. Well, what have we just proved there mathematically? We've proved that this thing isn't rising up off the floor spontaneously, nor sinking through the floor spontaneously. So now let's do sum of forces on the x. Well, it equals, and in this case, and we're dealing with up and down, not right and left. So that's right, I think. Yeah, that's my right hand. So all the forces to the right minus all the forces to the left. Terrible handwriting. Okay, in this case, what do we have? Sum of forces on the x equals 428 newtons to the right minus 0. Sum of forces on the x equals 428 newtons to the right. Oh, and the one, you know, the one step I kind of skipped there, let me remedy that. I didn't do the thing that I did on the other axis, where I actually wrote out what those forces were. So it's the force of eddy, which is the force to the right, and there is no force on the left. So 428 minus 0, net force on this object is 428 newtons right. Okay, so I'm starting to draw out a free body diagram for a problem. Now remember, the first step in the problems, because you're getting a verbal problem, is drawing this free body diagram. I'm starting from the free body diagram, so you have to become pretty proficient at drawing the free body diagram from a description. So I've got force of gravity on this object is 261 newtons down, force of the floor is 261 newtons up. I have the force of Hannah pulling on this thing, or pushing, we don't really know, at 511 newtons above the horizontal. And then who shall you oppose? Who shall oppose you, Hannah? We'll have you and Ireland battling this out. But Ireland's only exerting a force of 298 newtons. And hers is directed straight along the floor, 0-degree angle. Okay. Well, I've got my free body diagram, which would be my first step. I'm going to go for sum of forces on the y, which is all the forces up minus all the forces down. Is it 0? No, it's not 0, and here's why it's not 0. If we look at the force of Hannah, this is a vector that is not directly on an axis. So of the forces up, what do we have? Well, we've got, and I'm just going to sort of shortcut this. Well, I have force of the floor, and I'm going to do this. I also have force of Hannah on the y. So I'm going to use subscripting. And I know that both of these forces are up, so I want to make sure I'm adding them together. They're not in opposition, they're in the same direction. And the sum of those gives me my forces up minus my forces down. So typically with a problem like this, and I'm going to move my free body diagram out here. Oh, shoot. I would write a little note to myself. Force of Hannah on the x equals force of Hannah. Here's my angle. That's my adjacent side. What am I going to use here? Force of Hannah cosine theta. Force of Hannah on the y is going to be force of Hannah sine theta. This is just like the bookkeeping that you did with your non-perpendicular vectors, where anything that is not directly along an x or y axis has to be resolved. and you've got to come up with totals.